issues that we're finding within our understanding of physics. And trust me, I had a long week too, bro. So it's totally okay. We're just here for a conversation and a dialogue. And like I said, I really appreciate you for joining. So
Yeah, I'd love to have him ask him some questions if you guys are amenable to that.
absolutely, brother.
Well,
Dr. Cassandra, can
I
you
should
hear? I don't know. How do you want us to refer to you? I think most people call you Make
make line.
Make Line. Okay, but I like Make Line wrong
Uh,
again because that's Dr. Cassandra's whole position, looking for the truth. And if we're being deceived, we want to make sure that we weed out the misinterpretation. So yeah, feel free.
yeah, and I should a couple of disclaimers up front. Yes, I have a PhD in physics, but also that was a long time ago, and it's not what I do with my career anymore. So just take that for what it's worth. I'm not a practicing physicist, so I don't want to misrepresent that or claim that I could talk about physics in an advanced way with my brain having decayed over the years as I've gotten older. But I do want to ask Dr. Cassander, are you a flat earther? And you also have a PhD in physics, is that correct?
I am a what I call a fat earther. I believe in a almost globe, but I'm open to some of the arguments that I've heard since I've joined this group. Um,
Okay, so
and what was
you think it's an almost globe?
Yeah, it's got hills and valleys on the surface, so it's not a perfect globe. And
Right.
I do believe it has a bulge at the equator, but unlike mainstream, I believe it's caused by the ether wind, which by Bernoulli's principle would cause a drop in pressure over the equator, and with no wind over the poles, there would be a bulge produced by the ether wind. So you might say I'm an etherist,
Okay,
if
so
there is such a one.
just to set some context here, you have an enormous disagreement with someone like Sacred, right? Because Sacred would not agree with that. Am I just understanding the terrain correctly?
Yep, yep. For some,
Okay.
like, we agree on some
Yes.
things and some things we don't.
Okay.
But we have
And
found a lot of common ground when it comes to the lack of motion of the Earth. What's your position with that? Heliocentrism, is that your mainstream take? Is that your position?
Y yeah, I don't dispute what NASA says about the solar system for the most part. So my question to Dr. Cassandra is, so what is the I heard what you said about the fat Earth. Um, is there a specific proposal that you want like a peer reviewed journal to look at that they refuse to evaluate?
Well, I didn't submit it to a review um, journal because I've already attempted to post things on Wiki, and I've met up with a lot of resistance um, to anything that uh, goes against the mainstream party line. So I haven't even attempted to post to peer-reviewed journals. Even archive requires that you have a uh, academic position or someone who will uh, uh, support you. And I'm retired. You said that you've been quite a while away from physics. Well, I'm 84, so there's probably I'm even older in my physics training than you are,
Oh, good for you,
and
by the
I
way. That's
also
great. My
well,
dad just
thank
turned
you.
80.
All you do is keep breathing. That's the secret.
Getting old sucks, but it's better than the alternative, right?
That's right, exactly. Um, and I've been retired for almost 20 years, so I've also been away from physics in the sense that I don't meet with colleagues physically. I certainly do with over the internet, um, but I'm I'm not in that different a position than what you described.
Yeah, well, you've
So,
you've seen some really cool stuff over your lifetime in terms of developments in physics. I kind of envy you for that.
well,
I mean, when you
more in technology, more in technology than science.
sure. So is there a did you propose some of these ideas when you were before you retired, or did it come after you retired?
Oh, after retirement.
Okay.
What happened was I was totally mainstream when I graduated and I got my diploma because I had been indoctrinated. And I learned that if you had a different idea, well, you could discuss it in the classroom, but you better have the mainstream belief when you took a test. Okay, you couldn't use a test to uh, introduce any of your new ideas or to challenge any of the existing ideas. You would just be wrong. So it was only after I graduated that I had the freedom to investigate uh, other other areas of physics. I joined what are called dissident groups, those who, for one reason or another, are opposed to mainstream thinking. And I uh, gradually developed uh, first a rejection of evolution biology, even though that's not my field. The logic of evolution, uh, I can't I can't accept. And then I went on to geocentrism. I basically got into that because of religious reasons, because the Bible preaches nothing but a earth-centered world. And then I developed what I call the alpha model. Did you hear the discussion of that, or
No, I'm sorry.
did
I did not, but I'm listening to what you're
you?
saying. So you're
Okay,
go ahead.
the alpha model it stands for absolute lab frame. That's the ALF. It's the answer to Newton's bucket, where Newton uh, described that the lab frame, the frame that he was in, correctly predicted the observed vortex formation of the water rotating in the bucket, whereas a theoretical bucket observer, a bucketeer, if you will, who is stationed and fixed on the bucket, if he applied the laws of physics and applied centripetal motion, because the water is co-moving with the bucket, he would say that the water is not moving, centripetal force is zero, centrifugal force, sorry, is zero, and so the water should be flat. And that's the classic anomaly that Newton proposed in 1687. And that has not been solved in the 337 years since. Newton said there's an absolute reference frame, but that's purely mathematical, because if you ask what observer do I put at the center of your frame, your absolute frame, in order to prove it, he couldn't answer it. It was strictly mathematical. And Ernst Mach said that it's the inertia caused by the mass of the distant stars, and that would cause the rotation of the water. But if we reverse the argument and say, what if you were at the distant stars? Then the Earth would not be capable it would be rotating with respect to that distant star. But we know that the Earth is a valid inertial frame. The laws of physics are valid. So we come to the conclusion, that is, I come to the conclusion, that the Earth in dynamics is the only frame that you can use to correctly predict future motion. Of course, the mainstream thinking is that you can use any reference frame that you want anywhere in the universe, but if it's a rotating frame, you have to use the fictitious forces, the centripetal force, the Coriolis force, and the Euler force. But if you have to use those forces for a rotating frame, then it must be rotating with respect to some other frame that isn't rotating. And if I pose that question to any mainstream physicist, they can't answer that. So that's basically an outline of, well, the other FA part of alpha means fluid ether. All of the things that are predicted by Newton's law and Maxwell's laws, all of them can be, excuse me.
Make line. Do you have you studied or learned or had any research done about the ether?
No, like most physicists, I have not researched the ether because it was rejected in the early 20th century or late 19th century as being unnecessary. I did study electrodynamics, modern physics, nuclear physics, biophysics, quantum mechanics, and so on. My question for Dr. Cassander would be, and I realize he may have just left for a moment, so no worries if he can't answer, but is he claiming that the equations of either classical or relativistic physics are unable to explain the curvature of water in a spinning bucket? That math doesn't work? That'd be one question I have. I have several other questions. Another question I have is, does he have a different equation that correctly predicts the curvature of water in a bucket? And could we do that experiment in our backyard or our kitchen? Because when I was a lab instructor, we would do things with the undergraduates, like have a camera, and you could do simple things like toss a ball and click with your mouse, and see the parabolic projectile motion of something that's thrown, and you could use the equations of Newtonian physics, the law, like the law of gravity and that kind of thing, to accurately, measure like the gravitational constant, that sort of thing. You could measure the position, the velocity, the acceleration of a projectile, and there's just no ambiguity about it, right? You just, here's the equation, crunch the numbers, take the data, does the data fit the equation? So that seems to work, but he's saying that this experiment would not work using similar equations? Because I would be surprised if that was the case, but that sounds like what he's claiming, and maybe this is an ancient paradox that hasn't been solved, or maybe there is a solution that he didn't appreciate. But then again, that would also be surprising because, of course, he's been a physicist longer than I've been born. So I acknowledge that too.
It's not a contention with the with the correctness of the equations. It's the frames in which they apply to make the correct prediction. But real quick, before Cass gets back, we are now at $700. Ken has joined the pot as well, and there was a few others, so I got a list going. We're at $700 for the Alpha Challenge.
Okay, I have a very important question at this point. So people are donating money, and who keeps that money?
So right now I'm holding it.
And what happens after you hold it? Do you give it back?
Yeah.
Okay.
Yeah, if this doesn't
Yeah,
go
so
through or some period of time goes on, I'm just giving it back before the refund period. I'm not trying to get fucking.
I didn't know if this was a
No, this just like all came on
a fundraiser.
spontaneously. No, this
a
all
flat
just
Earth
came.
fundraiser.
No. This all just came on spontaneously. And yeah, if people don't answer the challenge within a month, like this is all being refunded to whoever put it up front.
Okay, so you're saying, and I realize we don't have the benefit of Dr. Cassander, so you're speaking on his behalf. I don't want to misrepresent his position, but it sounds like what you're saying is the standard equations of motion of classical physics will do the job. They will predict the curvature of Newton's, the surface of water in Newton's bucket, I think is what we're talking about. But somehow the conceptual explanation of what those equations, are, which reference frame they're tied to, you're objecting to that. Am I summarizing that correctly?
Nailed it.
Okay, so what I would say is physics, so in my experience, physics is so confusing and it's so error prone, right? Like our intuitions are really bad at predicting things in physics. I mean, sometimes they're good, but sometimes they're really bad. And so math is sort of like the referee. Math is the thing where you can't wiggle out of it, right? Like we can all pretty much agree if you write down an equation and then you solve for x, there's one and only one answer. And then if you do an experiment, and we all agree how the experiment, all the data is collected, and you measure x and then you compare it to the calculated x, they either agree or they don't agree. Typically, I mean, of course, there's lots of room for debate, lots of room for error, but that's sort of like the referee, right? Now, when you say, yeah, the equations you get x, and when you measure it, it matches x, the data matches x, but the interpretation is incorrect. When you say the interpretation is incorrect, that raises alarm bells for me because that says, okay, it is possible to have more than one interpretation of mathematics. That is possible. Like there's more than one interpretation of quantum mechanics, for example. But the one thing we can hang our hats on as physicists is this is the math, this is the data, and they agree or don't agree. I'm oversimplifying, of course. In reality, sometimes it's not that simple, but I'm saying generally speaking, the quote unquote interpretation, I have pause when you say, well, the interpretation is the problem because there's wiggle room in the interpretation. Like how do I know? It's hard to be precise about an interpretation, but an equation is very precise. Data is very precise.
Agreed. So, are you familiar with how Twitter works? And I completely agree with you on the math and the predictions and how valid that is, and it's kind of the referee, so to speak, especially in this alpha scenario. So, are you familiar with how Twitter works, or do you need like a quick tutorial, real quick, on how to get you to the jumbo?
I'm sort of conversant with Twitter. I do see the jumbo. I've never successfully posted to the jumbo, but I can see the jumbo.
Okay, cool. If you scroll all the way to the left, you'll see a post called Alpha Challenge, and then if you go back 2 posts from that, you'll see a post called Pendy. It's hashtag, so you'll see a hashtag Pendy, hashtag Energy Conservation, Lab Frame, and Pendy Frame. If you click on that, the images associated with that post will come up, and we could look at the 2 reference frames, the lab frame, the Earth, right, and the frame of the ball that's swinging on the pendulum, the bob frame, right? And we could say from the Earth frame, the pendulum is moving with respect to the stationary Earth, or from the Pendy frame, we could say the Pendy ball is stationary and the Earth is moving. When you get into a kinetic energy analysis of that for the potential
Described with the hierarchy. So there is a level of satellites result. So
I'm
it
using
isn't all,
super.
first our image is viable.
That was generated.
for dynamic energy predictions and predictions of motion and all that. This is where you would start to apply that.
You be the lead. Check.
All right, hold on, guys. Let me see if I can bring Proud back. I don't know if Dr. Bennett can hear me.
To the lab times divided by just the ones
Science, hey, stop.
Make line.
Make
and Newton's bucket. So
Does the data fit the equation? So that seems to work.
Free, so to speak, especially in this alpha scenario. So you'll see a hashtag Pendy, hashtag energy conservation, lab frame, and Pendy frame. If you click on that, the images associated with that post will come up, and we could look at the two reference frames, the lab frame, the Earth, right, and the frame of the ball that's swinging on the pendulum, the bob frame, right? And we could say from the Earth frame, the pendulum is moving with respect to the stationary Earth, or from the Pendy frame, we could say the Pendy ball is stationary and the Earth is moving. When you get into a kinetic energy analysis of that for the potential energy, what you'll find is that the only valid frame to do the analysis with is with respect to the stationary lab frame. If you try to use the pendulum ball frame and have the Earth do the work, when you use the mass of the Earth, you get a massively disproportional amount of energy that's not present. So this is a explicit mathematical proof that that in dynamics, right, if you're going to analyze the system's energy and conservation laws and all that, you have to use the lab frame, and it is absolute. Any other frame makes the incorrect prediction.
So what is the prediction specifically?
Prediction specifically is how much energy the pendulum has when it's swinging to precess, right? So basically you take the mass of the pendulum, the length of the cord, and the time it takes for it to complete an oscillation. And when you do all that, you will find that there's no excess potential energy or anything like that. And when you use the Earth frame, you'll find, because you're essentially basically what you're swapping out is the mass of the pendulum ball for the mass of the Earth. So you have a disproportional amount of energy that's not measured there.
Okay, so for example, just using like really basic equations of physics, if the height of the pendulum, let's just call it 0 when it's at the bottom, right? Then its energy is just the kinetic energy, right? So it's 1/2 mv squared. And you're saying you measure that and you get a number. And you're saying there's a different reference frame where you measure that and you get a different number. Is that what you're saying?
Mm-hmm.
Okay. But the energy, is the amount of energy is not the thing you're measuring, right? Like that's arbitrary because height is an arbitrary number. Energy, the law of physics is that energy is conserved. The things you observe are that energy is conserved. You observe things like speed and position over time, but you don't really like in like a high school setup, like you just measured, did this pendulum apparatus using like super basic physics. You're not really measuring energy, right? Like because the height is arbitrary. You could say the height is 0 at the bottom, or you could just say, well, actually, it's 10 feet off the ground. So then it has potential, right? Then it has potential energy, and that you can always add an arbitrary constant to energy. Like energy is not an observable in classical physics. It's a conservation of energy that everybody can agree on, but you don't measure energy. Like if you took a video camera, your video camera doesn't tell you the energy of that pendulum. It tells you its position at a point in time, and you can then plot that position over different points of time. And yes, you can calculate the energy, but there's no law of physics that says you're going to observe and calculate the same amount of energy, because you have to pick, like how did you calculate the potential energy of the pendulum, right? It depends on its height. Well, the height is arbitrary. Like where did you assign 0? Okay, but ignoring relativistic physics, right? Like
this isn't a relativistic issue though. And then on that,
so hang on, the equation for energy here that you're using is potential plus kinetic, right?
Yes.
Okay, so what's the potential energy? How do you calculate that?
MGH.
Okay. And how do you calculate H? How do you determine H?
Like you said, the difference between the bottom of the swing and the top of the swing, vertically measured.
Yeah, but you can always add or subtract a constant to the potential energy, and you get the same
Why?
motion.
If
Because
you
that's how the
if you
math works,
cha-
right?
No. How could energy be conserved if you're allowed to add a constant to the total energy?
Because energy is conserved over time if the forces are conserved. So in other words, if your energy at time 0 is the same as energy at time 1, right? But that doesn't mean that there's an absolute energy. Like, it depends on the arbitrary decision of what H is. H could be 0 at the bottom, or I could just decide that H is a plus 10. I could decide that my reference frame is far enough below the pendulum that H is 10 at the bottom and it's a 15 at the top. Or I could set a different reference frame and say that H equals 0 at the bottom and 5 at the top. And then your energy consequently would have an arbitrary constant, right? Plus or minus, you could add or subtract any constant and you get the same motion, right?
What if you use the pendulum bob as your reference frame?
Well,
Then-
hang on, wait. Do we agree with that? So what I just said so far?
No, I don't agree that you can add a constant to the total energy. The total energy is kinetic plus potential energy. And
Yeah, but potential energy
if
is
you convert that to heat energy, you can show that there's an equivalence between the heat and the radiation that the system produces, equivalent to the mechanical energy that you observe in the motion of the mass, the pendulum bob.
Okay, but I'm using super.
It isn't arbitrary about adding a constant, because then you're saying, is 15 equals 15? No, I can add a constant. And if it isn't equal to 15, I can add a constant to make it equal.
But you're saying,
No.
but the potential energy is proportionate to H, right? And H is the height. How do you determine the height? How do you measure that?
From the bottom swing of the swing to the top of the swing.
Yeah, that's only telling you the
vertically measured.
change. But yeah, but the difference in H from the bottom to the top is telling you the change of potential energy from the bottom to the top. It's not telling you what H is.
You define what H is.
Okay, how do you do that? Where do you call H 0? Where do you set H as 0?
I think this is the third time I'm saying it. The bottom of the swing is 0, and the top
Okay.
of the swing is vertically measured is H.
Okay, suppose that you did the same math, but at the bottom of the swing, you call H equal to 5. Let's say that it's 5. Let's say I raise the pendulum 5 feet in the air. Will the math and the experiment give you the same motion?
No, it's the difference.
If I take a
between the top
pendulum,
and the
if I take a pendulum and I raise it 2 inches up, am I going to get a different motion?
What do you mean by different motion?
The classic like pendulum motion, sinusoidal. Well, hang on. I'm just talking about things you can see and measure for starters, right? This classic sinusoidal, motion of a pendulum over time, right? It's distance, let's say, from the center, or just looking at a pendulum. What does that look like? If you raise it or lower it off the ground, that motion of that pendulum bob relative to its pivot point is the same, right? It's that classic sinusoidal pendulum motion, right? Assuming you don't change anything else. Correct?
H is the difference in the height, yes.
Yeah. So what's operative here, what sets the motion of the pendulum is the change in height from the bottom to the top, but not its absolute height relative to some lab frame.
No, in the lab frame, you can measure the height from the bottom of the swing to the top of the swing. You don't have to measure it from the laboratory floor.
Right. So what you've just said is the difference between H at the top and H at the bottom, right? That's delta H, right?
Yes.
Right. So when you use that to calculate potential energy, you're calculating the change in potential energy from the top and the bottom. That's what you just calculated, right? Okay. Yeah. That's what's operative in what you can measure. You can then use that to, do whatever you want to do, predict conservation of energy or predict the motion of the pendulum, but you have not set the potential energy. You could add an arbitrary constant and delta H would be the same, and the change in potential energy would be the same, and the motion would be the same. You can always add an arbitrary constant to the potential energy.
Hey, can I interject real quick? Because this is kind of getting off into the weeds a little bit. The main point about this is that the kinetic energy equivalence, right? So if we have the velocity squared is equal to velocity squared for the pendulum frame and or the earth frame, you would have to show dynamically that the forces using mass in both frames and would be equal to m in both frames, and it's not. That's what's producing the huge discrepancy here. The height of it isn't what's in question. You're kind of going down a non sequitur.
I didn't follow you, Alan. Sorry. What's the key discrepancy?
The key discrepancy here is we're talking the potential kinetic energy equivalence between the two frames, right? And we're saying that the lab frame distinctly makes the correct prediction for that when you introduce a dynamic analysis. So when you introduce the masses, right, which is what's changing the force that's applied there, when you use the mass of the Earth, you make the wrong prediction. You got to get back. Okay. You got to get back on track on that. It's 1/2 over mv squared.
Okay, so when I think of a pendulum and when I think of a prediction, I think of something you can measure. And when I would measure a pendulum, like typically in my mind, I'm thinking of you take a video camera and you measure the position of the pendulum at every point in time. You don't measure the energy, right? Like
listen, bro.
You can calculate energy.
In the reference frame of the pendulum is 1/2 times mv squared equivalent to the lab frame, where you would do the same of 1/2 times mv squared as well, right? Are those two going to produce the same output, or is one going to distinctly and uniquely make the correct prediction?
No, yeah, your kinetic energy, if kinetic energy is 1/2 mv squared, then different reference frames will give you a different answer, right? Like in my reference frame, my kinetic energy, if I'm standing still, is 0. But in the reference frame of a car going by my house...
Which one gives the right...
Got you. We're back on track. Continue.
Okay. When you say the right answer, to me, you have to measure something and then compare it, right? So we can disagree about what my kinetic energy is, but what we have to agree on is if you measure my position relative to my house, we're all going to agree that I'm not moving relative to my house. Right? That's what we agree on. We don't agree on my kinetic energy because velocity by definition is dependent on your reference frame. So we don't have to agree on that. Like physics doesn't say that there's an absolute velocity, nor does it say that there's an absolute kinetic energy in classical mechanics. It doesn't claim that. What it claims is that there's motion, and we always have to agree on them. Like everyone has to agree that the pendulum bob never touches.
It's not the velocity, broski. It's the mass, right? Mass.
Well, kinetic energy.
That's producing the difference in the force for the dynamic prediction there.
Well, sorry, hang on. You were talking about kinetic energy, and you were saying we get a different kinetic energy in different reference frames, correct?
Yes.
Okay, I agree with you. That does not entail different mass, because in one reference frame you could have a different velocity.
No, dude. So the pendulum is swinging at the same speed regardless, right? 1 second, I got a phone call. But the TLDR, right, is when you introduce the mass, that's what's going to change it, because the pendulum bob is not the same as the Earth mass. I'll be right back.
Yeah, I don't follow. Sorry.
Yeah, what we're claiming is not kinetic or potential, but total energy. The law of physics that's being claimed is that if you add the kinetic and the potential energy at any point in the swing, it will be constant. And we say that is verified by measurement in the lab frame. If you're in the pendulum bob frame, okay, so imagine that you're attached to the bob and you're looking down, you see the Earth moving back and forth underneath you. what is the kinetic energy of the Earth as measured in the pendulum bob frame? It's the mass of the Earth times the speed of the Earth, which is equal and opposite to the speed of the pendulum when viewed from the lab frame. Now, the mass of the Earth times the speed, the common speed, greatly exceeds any energy that you would observe in any pendulum. So the only correct application of conservation of energy is in the lab frame, where the total energy agrees with what is measured, where the total energy is defined as kinetic plus potential. If you go to the bob frame and try to measure the motion of the Earth underneath, you get a ridiculous answer where you have the mass of the Earth times the speed of the Earth squared over 2. And that, plus the mass of the Earth times GH, makes it total violation of the conservation of energy law. So that means that the lab frame is preferred for the conservation of energy, which is just one of the laws of physics.
Yeah. Okay. So I think I follow you. So yeah, so gravity is a conservative force, right? It's not changing over time. And if you choose the reference frame of the pendulum bob, just like if my car crashed and flipped over a bridge, right? And I like had a camera fixed to my face, you'd see this crazy motion outside my car, right? You'd see like this ridiculous spinning, crazy, like glass would be flying everywhere. And you would see non-conservative forces in that reference frame, right? That's kind of what you're saying. And so there's a reference frame that's much more cleaner mathematically because things are conserved.
Yes, and kind of no.
Yeah. I thought that was standard physics. I thought that was not unconventional to say that.
I would like to ask you a question, and that
okay,
would
don't
be,
quiz me because I will fail.
Well, it relates to what you said. You said when Alan asked you about ether, you said that ether was rejected by experiments that were done long ago. Could you remember what experiments rejected the ether and why?
Well, from my memory, there were a number of experiments that seemed to show that the speed of light is constant in all reference frames. And so Einstein took Maxwell's equations and basically assumed that the speed of light is constant, and then let everything else flex. And it turned out that Lorentz transformations instead of Galilean transformations of reference frame was a way to accomplish that. That's my probably incorrect, oversimplified memory.
Yeah, the ether was rejected because they thought that the Michelson-Morley experiment, which was supposed to test the motion of the ether through the
motion of the Earth through the ether.
Through the ether at 30 kilometers per second in its heliocentric orbit around the Earth, around the sun, that would be detectable by the interferometers at the perpendicular placed by Michelson and Morley, which would cause different paths of the ether to travel at different speeds, and then the interference pattern would be registered on an interferometer. And what they actually measured was something like 6 kilometers per second, and it fluctuated. And they claimed that represented a rejection of the ether, even though they measured a non-zero value for the experiment. And the experiment also provided an impetus for the rejection of ether by falsely claiming that the 6 was an experimental error, where the interferometer is one of the most precise instruments in measuring optics that we know of. And in fact, the threshold of detection for the ether was about 1,000 times lower than the value of 6 kilometers per second, which was measured in the experiment. So the training that you got from your description of MMX indicates that you were exposed to an interpretation. Remember, that's the word that I used. You were exposed to an interpretation of the MMX, which assumed that it was 0, because that's what it was called, null. But the actual value was 6 kilometers per second, and it fluctuated, which means it was a wave, not a constant value that was being detected. Experiments have been done since Michelson and Morley that allow us to see that even more of the ether was ignored in the original experiment, because it appears in what is called the Sagnac effect, which was used in 1913 to reject Einstein's theory by showing that the speed of light is not c, but c plus v, where v is the speed of the rotating disk that Sagnac used. So there is a basis for adopting an ether which underlies all of the claims that relativity now makes by using the Lorentz transformation to masquerade as responses to what are actually ether effects. So actually this was discussed by me before you arrived, that the students in physics today are exposed to what are not correct interpretations of the experiments, and that has been proven by experiments that were repeated of the MMX and showed that there is indeed a fluctuation in the ether. So I don't know what to.
Well, I'd be surprised that Caltech's LIGO experiment could measure length with their interferometer so precisely. If they got the speed of light wrong.
Well, it's not just
they can do it, but they just happen to get the right answer.
It's not only that, but check it out. They have to correct for annual periodicity variations and quote, they chalk it up as quote unquote seasonal, but this is what Dayton Miller measured. So like their measurement, they say is basically 1/1000th the width of a human hair. So the measurement that like this periodicity is much larger. So they're in in other air margins, et cetera. So they're obviously zeroing that out. That's not using LIGO as your proof, and then that's just not going to cut it here.
I thought it was a fraction of the width of a proton.
Oh yes, thank you for the correction. My apologies. It's actually 1/1000th the width of a proton. Yeah, otherwise known as a proti. You got your proties and your nudies.
But so Dr. Cassandra, I'm sorry, I'll drop it because I don't want to beat a dead horse too much. Maybe we've moved on and maybe I just didn't get it. But you're saying, it sounded like you had to leave a minute ago. And what I heard Alan say, and I'm not sure if this is what you're saying, is that, yeah, the law, like if you look at a pendulum, the laws of Newtonian mechanics, the math that we all are sort of familiar with, it will correctly predict the observed motion of the pendulum. But the interpretation of the quote unquote correct reference frame is somehow invalid. The math works, the experiments work, but the interpretation is what you're disputing. Am I correct on that?
Well, the motion of the pendulum, we would using as an example conservation of energy, but it could be any law of physics. All right, any law of physics that's derived from a Lagrangian. You know Lagrangian theory, right?
Yep.
Yeah. So any energy derived law of physics based on the Euler-Lagrange equations, when applied to motion in the lab frame, as viewed in the lab frame, will be correct. The laws of physics will be correct in the lab frame. But if you use a different frame, like the bucket frame, which is moving with respect to the lab frame, and you apply the same law of physics, centrifugal force, you will not predict the correct result. And that statement is not under dispute, because that is stated by Isaac Newton in the Principia, the Newton's bucket anomaly.
Okay, so are we focused on Newton's bucket and not the pendulum then?
It doesn't matter.
Okay.
We're focused on the laws of physics as applied to either the lab frame or a non-lab frame. If you apply the law of physics to the lab frame, you will get the correct result. If you apply the law of physics, the same laws, to a different frame, but the same motion, you will get the wrong answer.
Oh, okay. And you're saying this is why Newton said that there was like a correct inertial frame relative to the distant fixed stars? Is that what you're suggesting?
Well, that was Ernst Mach that said that. Newton said that there's an absolute reference frame that determines whether the laws of physics will be obeyed or not. But he didn't say, in the physical world, where should I put an observer in order to detect whether the laws of physics are correct or not? In other words, he pushed it off to a mathematical world where there is just a statement of a rule, but no connection with reality. How could you test what he said? He said there's an absolute lab frame, but I don't know where it is.
Yeah. So if you adopt the lab frame, we can all draw the force diagram, we can all do the math, right? And you're saying we get the correct curvature of a liquid in a spinning bucket, right? Am I correct so far? Okay.
Yeah.
Now, but within that theory, is there not a procedure to then say, okay, mathematically, what happens if we arbitrarily attach the origin of our coordinate system to the spinning bucket? And if we apply that mathematical procedure, are you saying that you now get a result that conflicts with the data?
Well,
because you get a very complicated result, right? I think.
You're saying if you do a transformation.
Yeah.
A coordinate transformation.
Right.
Okay. No, you must do a reference system change. Okay, that means you must move an observer from the lab frame to the bucket and make measurements in the bucket frame.
Right, which would be really difficult to do. But
well, you could use a larger model of the bucket. You could use something that could have a man on it, and you don't need a man. You can have a camera, like you said. You can use a camera to observe, fixed on the bucket wall, observing the surface of the water.
And if you did that, are you saying your camera would show you a result that is inconsistent with what you would calculate if you properly did that mathematical, reference frame transformation, and if you properly measured from that reference frame? Are you saying that they would be inconsistent?
not only I am saying it, Newton said it, and everyone else said it. No one denies that if you try to calculate the centrifugal force on the water in the bucket frame, when the water is co-moving with the bucket, you will predict that there's no centrifugal force because the water is not rotating in your frame of reference. And yet the water is distorted. The parabolic shape of the water surface indicates there's a centrifugal force, which is not predicted if you're in the bucket frame, but is predicted if you're in Newton's frame, the lab frame.
Okay, so you're saying that this is a known paradox of classical physics, where the data, it was sort of a lingering paradox that was never really resolved. Is that correct?
337 years.
Okay, and what would in your view, right? You have a contrarian view or a minority view. What is the majority view of physics to this? Do they not have an answer to this in your view, or do they have one that's incorrect?
Well, they have two that are disputed, which I went over with you. The Newton's absolute reference frame and Ernst Mach view of inertial forces on the bucket being causing it to inertial forces from the stars acting on the bucket that violate the centrifugal force law.
You don't think
But yes,
like general relativity addresses this? Like if you have a proper formulation from a general relativity perspective, and I'm not a relativist, I didn't study advanced general relativity, so I don't know the answer. I'm not qualified to opine on it. But they wouldn't say that, yeah, this is one of those things like the what's it called? Like the black body catastrophe, right? Where quantum mechanics, it turns out quantum mechanics can explain some really weird result of classical mechanics. You don't think that relativity goes back and somehow explains this?
no, I think relativity applies in kinematics, but not in dynamics. And that's where it's trying to be applied.
Okay.
When we talk laws of physics, we're talking dynamics. When we talk measurement of the surface of the water, that's kinematics. So what we're failing to distinguish is that relativity only is valid in kinematics, but not in dynamics.
And you're saying Mach's principle is, you don't think it's correct?
Well, a lot of people don't. Newton didn't think it was correct, and I don't see any consensus in the physics literature that supports either one of those.
I thought that generally speaking, general relativity is not, maybe not perfectly, but sort of generally consistent with Mach's principle, or at least takes it to a more, modern stage. I thought. Again, I'm not a relativist. I didn't study advanced relativity.
Well, besides challenging the concept of inertial frame as being any frame in which the laws of physics are obeyed, I challenge special relativity. In fact, I just did a talk about a week ago where I went over Einstein's train. You say you haven't studied relativity. Are you familiar with the simultaneity?
Yeah, I remember Einstein's train. Yeah.
Okay. So I did a mathematical analysis of the train when it is parked at the station. Okay, so the relative speed between the lab and the train is 0. And then I considered the motion of the train at speed v and compared the energy of the train in the lab frame to the energy of the Earth as seen from the train frame. And when I calculate that, I get the same problem that that I described with the pendulum, that the mass of the Earth in the calculation compared to the mass of the train makes the discrepancy obvious. There is no correspondence to what you measure or what you predict in the train frame compared to the correct value for the energy of the train in the lab frame. So there's a consistency in all of the experiments in comparing what you predict in the lab frame, which is correct, and what you predict in a non-lab frame, which is incorrect. Now, I showed that if you apply special relativity, that is, as you said, the speed of light always equals c, the conclusion is that the speed of the train has to be 0. So special relativity is valid in a model in which the train and the lab are at rest. Special relativity is not valid for relative motion between the lab and the train.
And you said that you began departing from conventional physics when you learned that the Bible is geocentric, and so you rejected heliocentrism for that reason? Did I hear that correctly?
Yeah, I would say that was what motivated me to consider geocentrism. And then I looked at the science, and I found that that was lacking in its fundamental logic. And so
So you think the sun is orbiting the Earth?
Yes.
Basically, they're not orbiting their center of their common center of mass?
No. No, the Earth is the center. The lab frame indicates that there is a preferred position. Contrary to the Copernican principle, the Earth is a preferred location in the universe because, for the reasons I just discussed, the laws of physics are valid when you're on Earth, stationary, and not valid if you're moving with respect to the Earth.
But and you're saying is Newtonian gravity, not just sticking with like Newton's laws, just gravitation. So for example, you can see the moons of Jupiter with, I think, binoculars, but certainly a telescope, certainly a satellite. Those moons that are orbiting Jupiter, they're not attracted. I mean, I'm sure they are attracted to the Earth, but they're basically due to the gravitational attraction between the moons and Jupiter, right?
Yeah, well, gravity is an effect of ether motion.
Okay.
That's the model. So
I guess what I'm saying, like what I'm getting back to is, do you think that Jupiter and its like moons what are they orbiting? Like they're not exactly orbiting the Earth, right? Because the Jupiter's moons are orbiting Jupiter.
Well, you have a hierarchy. You have the Earth, which has 2 satellites, the sun and the moon. And then
I was going to say, what's the second one? I was at a loss.
What the moon and the sun. And then those are the primary satellites of the Earth. The secondary, the moon has no satellites. The sun has, well, depends whether you treat Pluto as a planet, I guess. 8 or 9, no, 7 or 8 planets. And then that's the second level of the hierarchy. So they are the level 2. And then you have the moons of certain planets, which is the third level, and the stars. So this is called the Tychonic model.
But
Tycho Brahe.
Oh, sorry. Go ahead.
The objection to Copernican's heliocentric model and Galileo's agreement was provided 40 years later by Tycho Brahe, who introduced the model that I just described with the hierarchy. So there is a level of satellites, different levels in the model, and they're all governed by the motion of ether vortices, which keep them in motion. And that's the way we can explain circular motion by the motion of the ether, which we can't see, just like we can explain the motion of things like the leaves in a tree. We can explain them as the wind, which we can't see. Well, we can't see the ether either, and we can use that to explain logically the motion of cosmic objects.
Well, Dr. Cassander, you know, I can't right now verbally evaluate the math. In fact, even if you put the math in front of me, there's a good chance I would get it wrong. But use, you know, since we're using words, right? I'm trying to use, okay, what kind of evidence can I glean from this conversation? And I guess what I'm coming to is, you know, NASA can launch a probe and crash it into an asteroid. And so it seems to me that whatever math they're using is really good, right? It gets you really accurate predictions of the motion of an asteroid and the motion of projectiles launched from Earth. And it sounds like what you're saying is you have better math. So couldn't you or shouldn't you use that math to improve, you know, astronomical observations like Tycho Brahe did, right? Like take your math and say, hey, the position of Mercury should be here, not there, right? And then have people go use telescopes and look at it, or have NASA, you know, more accurately aim their probes, right? Because it sounds like the existing math is super accurate, and you're saying it's totally wrong, right? But how are they able to hit those asteroids if it's that wrong, you know? And if your math is better, shouldn't you be able to help them hit the asteroid even more precisely, right?
Let me ask you this. In what reference frame do they navigate in space? How do they calculate the motions of spacecraft? What
No idea.
frame?
I'm not a NASA engineer. I would assume that they would pick the most convenient reference frame, like the center of mass of a bunch of objects, or the biggest mass.
Well,
I would assume, but I don't know.
I think you're either sitting or standing on it. They use the Earth. Okay, the proof is the antennas that they use for navigation, for detection, and for sending and receiving signals are located on Earth. So the detectors define the reference system because that's where the data is collected. So they are getting the right calculations because they're doing what I proposed, using only the lab frame. Lab being used in a generic sense, the Earth at rest, or the ECEF frame. And so the answer to your questions, why don't they get wildly wrong answers? They're using the right reference frame. They're using the Earth.
So you think if they, like if NASA was located on Mars and they launched a probe from Mars to Earth, they'd get it totally wrong using the same, because they'd have the wrong reference frame?
If they use Mars as the reference frame, yes.
They get it wrong.
Yes.
Okay. So like if NASA sends a probe and it's orbiting, you know, a moon of another planet for a while and then it decides to descend, they're only going to be successful if they're doing all that math in the reference frame of the Earth, even though it's very far away from the Earth, and you could probably do all that math in the reference frame of the local moon, because that's the biggest massive body. They're like, once you're in orbit of like a moon of like Jupiter, I suspect that you can just pretend the Earth doesn't exist, and you would just pretend like Jupiter is the center of the universe, and I bet you're gonna land that probe where you think it's gonna land.
As long as you.
That's what I suspect.
Yeah, but you can't prove.
Well, I can't prove, but I'll I can't prove it right now, but I have a sneaking suspicion that if we call NASA, they would agree with me.
Lamau, nice dude. Appeal to a fictitious phone call, bro.
Well, we can't do math on this Twitter space, right? Like we don't have, a projector screen. So,
Well, really quick,
Hey.
Nick Lyon, I do want to say before Piezo jumps in, I did send you a paper by Luka Popov. We talk about this paper all the time. Are you familiar?
no.
There's a geocentric equivalence, even appealing to Newtonian gravity. And they go through all the math.
But doesn't it sound like ghosts a little bit? Like the ghosts are there, but never when you turn the lights on. It's like, well, NASA will always get it right because their interpretation was wrong. I mean, isn't that an amazing coincidence? I'm
Dude, I wouldn't even go as far as to accept anything from NASA because you can't verify the chain of custody for the data that you're getting. So like you wouldn't even know if all that was dog shit and just simulated anyway for, propaganda purposes. So I wouldn't even invoke that as like my proof, right? Because there's been experiments done on Earth like Michelson-Morley that falsified Big G, which is like, the causal mechanism of why things move in the sky. Because all they really have is everything in the sky obeys Kepler's laws, which is just a ratio of a periodicity over a constant. And when you introduce big G as a constant and you use big M as a constant, so like the mass of the sun, for example, once you've established those, all you're doing is getting the same ratio of periodicity over a constant. So that's why those things match up. It's not due to gravity. So if all that was just fictitious, right, and they were just simulating stuff on a computer and then outputting that, all of those calculations would, be completely satisfied and look valid, but you wouldn't be able to validate the chain of custody on any of that. So we don't accept that as evidence. We have interferometric measurements that show that the Earth is not moving at the velocity required for gravitation to be accepted as like the causal mechanism, as a mass attracting mass, or conserved into a gravitational field to cause the bending and warping of space-time to facilitate the motion.
So what I'm hearing, let me just repeat this back to make sure I'm getting this right. What I'm hearing is the laws of, let's just say the laws of Newtonian gravitation, okay, to a good approximation, are fundamentally wrong. But also, if you use those laws, you're going to get the right answers because you just happen to use the correct reference frame. But also, if you use the wrong reference frame, you'll also maybe get the right answers, but you can't trust the data because we don't have chain of custody from NASA. So it sounds like, to me, it's impossible to falsify this alternative hypothesis.
No. Listen very carefully.
Okay.
Kepler's laws are based off of a periodicity, right? When you introduce constants, i.e., G and M for mass of sun and the gravitational potential between any other body, when you run that G, MM, R squared equation, the masses cancel out and it's just a ratio of the constants and the periodicity. So the output is always going to match, right? Now, when you get into an actual experiment on the ground in the lab frame, like Michelson-Morley, Michelson-Gale-Pearson, etc., you find that the measured velocities do not correspond to 30 kilometers a second. So when you get into further extrapolations of things in the sky of like, oh, we sent something to the asteroid belt or whatever and crashed it into an asteroid based off of these equations, there's no possible way that any of us could verify any of that ourselves. What we have, though, is experimental falsification of Big G.
Well, you can verify it with the video that they took from the probe that crashed into the asteroid.
So again, you're not catching the
You're saying they faked the video?
Yes, we have no way to verify the authenticity of that.
But you're
right?
Oh, come on.
But hang on, but anytime you say,
hold on 1 second, dog. Edgelord, this is not a conversation for you to interject in. If you open your mic one more time, you're immediately gone.
I'm not trying to be obstinate. Honestly, I'm trying to like just understand the parameters of what
you're fine.
saying.
You're fine. It was the other guy. You're fine.
Because you're saying we don't have chain of custody, so we can't prove it. Okay, technically that's true of a lot of things, right? But fair, that's true. If they were faking it, if NASA faked that video, you couldn't prove that they didn't fake it if you don't have strict chain of custody. Okay, I accept that.
Yeah,
but
you couldn't
the alternative.
Well, you couldn't prove it's real.
But right, but you always have two. You have to weigh two alternatives, right? If it was faked, then you have to believe in like this massive conspiracy. Like I know people who worked at NASA, and they're pretty boring.
Yeah, so those people wouldn't have to be in on anything, right? The data is coming in simulated. They have a job there. They're working with data. They don't know.
But when I see an image of a control room for a satellite, I see like a huge room of people, not like one person controlling everything.
Yeah, and they're looking at monitors, getting data from somewhere that they can't even verify the chain of custody on. So they're not in on anything. They're just collecting a paycheck and doing their job and interpreting the math and stuff in the way that it should be. So like,
fine. I'm just saying when you say I reject that video because we don't have chain of custody, I'm just saying you have to believe in a huge number of assumptions about a really magnificent conspiracy. Like someone made a bunch of monitors in Houston light up a particular way and fooled a bunch of NASA engineers is what you have to believe. And that's equally implausible. Like to me, it's quite plausible that NASA actually did crash a probe into an asteroid. And you're saying, well, I don't have chain of custody, so I'm going to believe this really implausible theory that all the computers and all the engineers were fooled.
Hey, but before you go any further down that rabbit hole, because plausibility is a subjective term, I just wanted to make sure that before you leave here, because I don't know when you're lying or when you're leaving lying, there was a point that Alan made earlier, and it was actually Cassendar's whole point, and it actually surprisingly got glossed over and not brought back up. It kind of got exhausted, I suppose, by other things. But the point was in the mathematics of the pendulum situation and the bucket situation. But it applies in both because, you know, one's kinetic energy, 1/2 mv squared, and the other centrifugal force, mv squared over r. When you use the equation for kinetic energy of that pendulum, 1/2 mv squared, the v is going to be the object that's moving, right? So if you are in the frame of the Earth and the pendulum's moving, you'd say it's the velocity of the pendulum. If you're in the frame of the pendulum and you think the Earth is swinging around you, it would be the velocity of the Earth. Either way, the v is the same. Alan pointed that out. But then he told you, he said, what's not the same is the m, because in the frame of the Earth, the mass is the mass of the pendulum. But in the frame of the stationary pendulum, the mass is the mass of the moving Earth. So in the distinction between these two frames is not kinematic, it's dynamic in that they produce or predict different forces, massively different forces. You said, I do not follow when he said that to you.
Yes, so I follow what you just said, right? But I guess what I'm saying is, if you had a force of gravity, and if the Earth was gigantic and you had a pendulum, then mathematically you would predict that that same force would appear very different in the reference frame of the pendulum. You would get that as a consequence. So it doesn't, the fact that happens doesn't.
Yeah, but there's no variable for gravity in the kinetic energy equation. It's just mass and velocity squared. There's no g at all.
Yeah, sure. But like in classical mechanics, what you measure, like what determines whether a theory is true or not is the measurement. And you don't measure energy.
Correct.
You measure positions over time relative to a. Right.
You can measure mass and velocity, and what is energy? What energy is just related to work. You can measure energy through work. I mean, if you kinetic energy, right? So
sure. But let's not just for a second. Let's pretend that the entire universe is the pendulum, right? In that universe, you don't measure energy. You measure the position of the pendulum bob at various times. And the question is, what do the observers see? And what they're gonna agree on is the relative position of that bob relative to its pivot point. They're always going to agree on that. That's the point. They're not going to agree on its energy.
Yeah,
Right.
the kinematics are going to be the same, sure, but this is a dynamic argument, so I mean, repeating that the kinematics are the same, no one's disputing that. But what you could do is at the bottom of the swing, where it's 100% kinetic energy, at the moment that it crosses that bottom point, you have it smack into another object and commit a kinetic energy transfer, perform work on that other object.
Yep.
You can take an object of known mass and see how far it gets pushed when that pendulum hits it. Now,
Yep.
calculated based on the prediction of the mass of the pendulum, you'll get a result that agrees with what you measure in the lab. But if you use the mass of the Earth, you should have that thing get knocked out to Jupiter, and it doesn't. That shows you that their only viable frame to make dynamic predictions is the Earth frame, which is the absolute frame. It destroys the frame equivalence, which is a necessary concept for relativity to be true.
Well said.
Well, there's always, so like in classical physics, there's always reference frames that make forces conservative and that make the motion much simpler. You can always also similarly pick a reference frame that causes a conservative force to appear not conservative and makes the motion extremely complicated and very difficult to calculate. That's well known. Like if you open up a graduate level physics textbook and that's why at the graduate level in classical physics, you don't just use x and y and z coordinates. You start to use like r and rho and phi coordinates, right? You use different coordinate systems because the math becomes much easier. So yeah, mathematically there are going to be reference frames that are much simpler because of the fact that you may have an extremely massive object and objects attract, right? So like the reference frame, for example, the classic example is two-body motion and gravitation. The most elegant reference frame to choose, which will make the equations make sense, which will make, in which energy is conserved and the forces are conserved, is if you set your origin of your coordinate system at the center of mass of the objects, or if you have some complicated object that's spinning and projectile motion or whatever, same thing. You pick your origin at the center of mass, and so many things become much more mathematically easy to calculate and elegant, and energy will be conserved and forces will be conserved. That's all known. You'll learn that in classical physics. And if you don't pick that, if you pick some different reference frame, it'll be much more complicated. Those forces no longer appear conservative. You may have so-called fictitious forces and so on. But that is a consequence of classical mechanics. Like if Newtonian gravitation is true, then it follows that there's much more elegant reference frames. Like for example, but it wouldn't be the Earth. It would be the center of mass, for example, of like the Earth-Moon system, as an example.
Okay, but I mean, I
But like
can appreciate
that's not a contradiction of classical physics.
Well,
That's a
my point
consequence.
was, to be fair, my point wasn't that there are frames which are easier to describe things in. I was more pointing towards the postulates of relativity, in that all inertial frames show that in all inertial frames, the laws of physics are equally valid. And, this is the pendulum is just an example making a demonstration that while you can make completely equivalent kinematic predictions and kinematic measurements when you involve only motion, when you bring it into the realm of dynamics where forces are involved, you can objectively measure these forces and show that the only frame which makes the correct prediction is the Earth frame, which tends to show, right? Logic tends and dictates, therefore, that is an absolute frame, since in all other frames, the laws of physics will not hold valid, even though you can define them as inertial frames. But then when tested dynamically, the relationships established by physics equations, such as kinetic energy, centrifugal force, etc., do not hold true. Like, that's why the example of his pendulum is very simple and eloquent, because when you change it to, like you use Mach's principle and say, instead of it being, the pendulum moving about the Earth, it's the Earth moving about the pendulum. Whenever you plug in the big M for Earth instead of the little m for the pendulum, use the M of Earth, right? And you have that pendulum strike another object and perform work on it, the mass of the pendulum predicts that that object will move a little bit. The mass of the Earth predicts, like I said, that that object gets knocked out to Jupiter. What actually happens in the lab, though? It just moves a little bit, which shows that we now know which frame is dynamically correct based on the equations.
Sorry,
The
you're
two
saying
frames are not
if
equivalent
you
dynamically.
if you mathematically change your frame of reference to fix it to the pendulum, you're saying that you will calculate that you know, the pendulum knocks another object out to Jupiter. That's what you're saying? I'm not sure that's
If you
accurate. Is that
replace
accurate?
the little m of the pendulum, if you change the mass of the pendulum to be the mass of the Earth, and then calculate how much kinetic energy is in the system, that's the amount of kinetic energy that would be striking the object and performing work on it, which is like a billion, trillion, whatever the number is, times more.
Yeah, but you've
It's not conserved.
okay,
Energy
so
is
I,
not conserved between the
yeah,
two
but
frames.
I think we've gone wrong here. Is from the very beginning, the system has an asymmetry. The asymmetry is gravity is a force that points towards the center of the Earth and a tiny force that points towards the center of the pendulum. So you're starting out with like that force doesn't just point in any direction. It points towards the center of the Earth. Like that is true, just mathematically. So there's going to be a convenient reference frame. Now, if you switch to a different reference frame, like again, like if you imagine my car flips over a bridge and you just fix a GoPro to me, the background of my, you know, in my reference frame, there's all sorts of crazy motion happening. Glass is going everywhere. My Pepsi is like floating in the cabin of my car. But that's because, but like that is what you mathematically get if you apply the conventional laws of physics, like laws of Newtonian gravity, in a situation where you had an asymmetry. So of course, like there's going to be weird reference frames that you could pick, and the motion now becomes weird, and the forces are no longer conservative, and energy is not conserved. That's true. Energy is only conserved when the forces are conservative, and gravity is a conservative force. But like I just don't I don't follow you that if you change your reference frame, you're going to get a result that contradicts experiment. I'm not sure that's true. You can get a very difficult to calculate result, and the forces may be really weird.
The only forces you would have, as you admitted, I mean, we're neglecting the force of gravity because it's perpendicular to the force imposed by the pendulum striking the object, because at the bottom of its swing, it's hitting it horizontally, whereas the force of gravity is vertical. So those are in two completely different vectors anyway. One's in the x-axis and one's in the y-axis. So we're not concerned with the y-axis. We're only concerned with the x-axis at that moment when it strikes. So even that extra force wouldn't make an impact on the x-axis force. So it would still only be determined by F equals 1/2 mv squared, or sorry, kinetic energy equals 1/2 mv squared, and that would determine the work that can be performed on the object being struck. And you don't need to even take a very precise measurement to know that the mass of the pendulum versus the mass of the Earth is going to produce a very different result.
Sorry, why is the mass of the Earth relevant if the Earth's not the thing striking the object?
Because when you use your kinematic equivalence, once again at the beginning, if we say the pendulum is swinging about the Earth, or the Earth is swinging about the pendulum, right? If we do that, then what is the object that's moving? In the frame of the Earth, the object that's moving is the pendulum. In the frame of the pendulum, the object that's moving is the Earth. So the v, right, when you use v and 1/2 mv squared, the v is the velocity of the moving object. The m is the mass of the moving object. So whichever object you pick to be the moving object, you use that object's m and that object's v. So in the frame of the pendulum, where the pendulum is stationary and the world is moving around it, if you, in that frame, use the equation of kinetic energy at the moment that the pendulum is struck, you have to use the mass of the Earth, and that mass produces kinetic energy that is many orders of magnitude greater.
I don't think that's correct. I think if you fixed a GoPro to the pendulum, right, and so you're just watching the pendulum, in that reference frame, the Earth can be neglected. The Earth just generates a giant field of gravity that's pointing in a particular direction, right? That's causing its motion. But in its reference frame, all it's going to see, if you assume that there's this other object sitting, at the bottom of the pendulum's motion, what the pendulum bob will see is this arcing object rushing towards it, right? And when they strike each other in that reference frame, what it's seeing is the object striking it, the bob, at 1/2 mv squared, where m is the mass of that object and v is its velocity towards the bob. The Earth you can neglect, right? The Earth is only relevant insofar as it creates, you assume that it's this huge, you assume that it creates like an approximately static force field of gravity, right, in the lab frame. But in the frame of the bob, it doesn't strike the Earth, it strikes the object, and the object strikes it at the mass of the object times the velocity of that object in the bob's frame squared.
Is the object sitting on an object that's attached to the Earth, right? Like
I'm pretending the object's like floating somehow, like stationary in the bob's path, right?
Yeah, but it's not. It's just sitting. It's in the same frame as the pendulum support, which is fixed to the Earth. It's just sitting on the ground.
Yeah, sure. It's sitting on the ground.
Strikes it.
And the bob strikes it, right? So what the bob sees is this object curving towards it, and then they collide.
Right.
And when they collide,
and the Earth is behind it, pushing it, right? Because it's sitting rigid on the ground.
Well, it's irrelevant. It's irrelevant. I mean, the Earth is irrelevant, right? To the motion, the collision of the bob and the object simply depends on, if you're talking about the bob's reference frame, the mass and speed of that object. That's what it depends on, right? And what it's going to see is this object curving towards it, right? And in the bob's reference frame, it looks like the object is has this weird curve trajectory, and they're going to collide, and the energy that the bob, I guess, feels, quote unquote, has nothing to do with the mass of the Earth. It's 1/2 the mass of the object it's colliding with, the object, right? M, little m, and the speed of that object relative to the bob squared. And then what it's gonna feel like is that they have a collision, they ricochet off each other. That's what it's gonna feel like. And by the way, there's a weird force that it's experiencing. The bob is gonna experience this kind of strange force in the tension of the core that's holding it to its pivot point, right?
And if the object that the pendulum collides with is the Earth, like if it's just smacks into a rock, like the side of a mountain,
Yeah, like an infinitely large object. Yeah.
Yeah, I mean, if it just smacks the Earth, it's not going to just careen off into oblivion. It's going to just bounce off a little bit, because once again, the truth of the situation dynamically is that the only thing that's moving is the pendulum. The only mass that matters is the pendulum's mass. There's an absolute space, and in that absolute fixed coordinate system, the motion that's occurring is the motion of the pendulum and no other thing. Otherwise, we would use the mass of the other things that are moving in the pendulum frame, and they would work equivalently. There'd be a dynamic equivalence, but there's not. There's only a kinematic equivalence when we talk in terms of forces in this situation.
Okay. You say that. I'm not sure. I'm not sure I follow you, but to each his own.
He not only said it, we showed it mathematically.
I don't think you did show it mathematically, because again, the energy of an object that collides into you is 1/2 mv squared, where it's the mass of the object. Like if that object is sitting on Earth without friction, it doesn't matter. Like it could be hovering, and the result will be the same. It doesn't matter. The Earth's mass doesn't matter. I mean, except for the fact that it's creating the gravitational field, but
yeah, I agree that dynamically there's no equivalent frame to the Earth.
Like two billiard balls on a pool table, right? When you do the math when you do conservation of momentum and conservation of energy, what's relevant is the mass and the speed of the billiard balls, not the mass of the table. The table could be super heavy or it could be super light. As long as there's not much friction, what matters is the mass and speed and angle of the billiard balls that are colliding, right? It's the same thing
but
here.
Both billiard balls are moving with they're both moving independently of the Earth, and I said if the pendulum strikes the Earth, right? If it just smacks into the ground,
Okay,
right?
that's a different scenario, right? Now you're talking about hitting the earth, not an object.
I did say that because when we sit and watch it, if I let go of the pendulum and it smacks into the side of a mountain that's just anchored into the Earth, we might as well. It's rigid enough to be considered part of the Earth,
Yeah.
right? Then if I use the mass of the Earth to get the kinetic energy in the system, I would expect that pendulum bob to get launched into space because it just got hit with a Louisville Slugger the size of Earth, dude. Like that doesn't happen. And the fact it doesn't happen shows that there's only one valid frame to make the correct dynamic prediction, and that's the Earth frame, which is equivalent to absolute space.
Got out to the absolute frames out there. Sorry.
But I think in that case, you'd use conservation of momentum. And what you would find is that the billiard ball imparted a very, very tiny amount of momentum to the gigantic Earth, right? And the Earth is gigantic. So an incredibly tiny change in its speed would be an appreciable change in its momentum. And
I'm Jonathan Finiak.
Couldn't do it without the squad, man.
Earth, it would be the center of mass, for example, of like the Earth-Moon system, as an example.
Okay, but I mean,
but like that's not a contradiction of classical physics.
Well, that's
a consequence.
Point was, well, to be fair, my point wasn't that there are frames which are easier to describe things.
Like I just don't. I don't follow you that if you change your reference frame, you're going to get a result that contradicts experiment. I'm not sure.
In the frame of the pendulum, the object that's moving is the Earth.
Velocity of that object in the Bob's frame squared.
Is the object sitting on an object that's attached to the Earth, right? Like
I'm pretending I'm pretending the object's like floating somehow. Like
once again, the truth of the situation dynamically is that the only thing that's moving is the pendulum. The only mass that matters is the pendulum's mass. There's an absolute space, and in that absolute fixed coordinate system, the motion that's occurring.
Now you're talking about hitting the Earth, not an object.
As well as the energies. So you can impose the force on the pendulum, or the force the force of the produced by the Earth on the pendulum, or the force produced by the pendulum on the Earth to make different predictions. We can verify that it doesn't work when you use the force produced by the Earth on the pendulum, because that force would be so massive that you'd never see that pendulum again.
I don't agree. That's not what Newton's laws say. Newton's laws would say in this case, I mean, the dynamics of how they would collide would depend on a lot of details, but what you can say universally is that momentum would be conserved. That's what you can say universally, right? Energy might not be conserved depending on a whole bunch of factors, but in this case, if we have a really, really massive object, colliding with a less massive object, the one thing you would say is that linear and angular momentum will be conserved in Newtonian's laws, right? And here, that does not entail the billiard ball being, ejected into, to the moon or something. It does not. It just doesn't mathematically, because like in the initial state, right? All things being equal, let's just say the Earth is at rest in the Earth's reference frame, and you're looking at the billiard ball. The billiard ball has a relatively tiny amount of momentum, right? It's mv. In the end state, the laws of physics would predict that there must be the same amount of momentum, because momentum is conserved. It must equal mv. So you'd have to calculate what is the new momentum of the Earth and what is the new momentum of the ball. Well, if the ball is stationary, if the ball just, basically bounces just a little bit, that means the Earth must now no longer be stationary. The Earth moves a little bit. Well, it'd be very difficult to measure that because the change in velocity of the Earth would be tiny. Like if you whatever, let's say the momentum of the billiard ball at the beginning is 1. Let's just call it 1. For the Earth to go from 0 to 1, its change in velocity would be tiny because its mass is huge.
I mean, would it
So you
be
just
fair to
wouldn't
say
notice.
imperceptible?
But you could do. Well, no, because what
like,
you would do.
like you
So
could
if you wanted to
calculate
test
it, right?
this,
But this is
yeah.
like
But if you
an
wanted to test,
imperceptible.
if you wanted to test this, what you would do is you just take a pool table and you take a really heavy bowling ball, right, and take a much lighter ball, and you could do all sorts of experiments. Undergraduates do it all the time. And what you would see is that conservation momentum is the thing that's obeyed. And if you have a small ball that hits a big ball, the big ball's velocity changes a tiny amount, and the little ball slows down dramatically. And in the case of the Earth, you have an extreme case of that, where instead of a bowling ball, it's a gigantic planet. So the change in its velocity is even tinier than the bowling ball. You could do that on a tabletop.
Well,
And that's like a little miniature case of what you're talking about.
the
That's
energy.
not a violation of anything.
No, but energy is not conserved between the two frames. And the thing is what is energy? You can relate energy to work, and you can definitely calculate the amount of work, which is just force times distance, imposed upon that pendulum, right? And if you use that equation, you can tell which is true, and they don't make the same prediction. Like, they just objectively don't. Like, there's so many orders of magnitude different than each other, you don't even need to put specific numbers. It's like billions of times different. And we can very easily tell which one is right, and it's the Earth frame. So the thing that's being contested here is the existence or non-existence of absolute space. We posit that absolute space exists, and it can be measured and verified as such. And when you take these measurements, that's what it shows. So thus, since only the absolute frame makes the correct prediction, therefore there's no equivalent frame. There's no, like, all inertial frames are valid. There's none of that. There has to be one absolute frame that makes the correct prediction, since there's different predictions made between the two frames and one matches what we see.
Well, okay, hang on. If we're talking about an elastic collision, okay, so let's ignore like the ball is made out of mud and it sticks to the other ball. Okay, let's just say they're perfectly hard spheres. So it's an elastic collision. Okay, let's ignore an inelastic, or like it's an egg, right? And an egg breaks. Let's ignore that case. Let's just call it two very hard spheres. You could do the math very easily. You could do the experiment very easily on a pool table and just say, hey, what happens if I just take the 8-ball and throw it into this big bowling ball? Or what if I take an 8-ball and throw it into a much smaller ball? And you can pick any reference frame you want. There's a procedure, there's a recipe to take the standard laws of, Newtonian motion for an elastic collision, and you can transform that in any reference frame you want. You're going to get the same result. Now, if you want to take the special case where you have a very small object colliding with a very large object, right? Like the 8-ball colliding with a big bowling ball. If you mathematically just crank up the mass of that bowling ball, what you're going to see is pretty much every time the small ball, ricochets off the big ball barely budges, right? It's like not going to move at all. If you crank that all the way up to the size of the Earth, that's what you're talking about. That is the result you would see. Now, theoretically, every time you jump up and down, or every time you like throw a ball on the ground, technically you impart a tiny amount of momentum, to the Earth, theoretically. But it's the mass of the Earth is just so large, you would never see it. But you can see it in these experiments I'm talking about. And nothing about that there's nothing about that says, oh goodness, like the math that we do from classical Newtonian mechanics is at odds with the data you would collect if you watched the positions and speeds of all those spheres. That's just not the case. You could do this very easily. So your idea that, like, well, a ball runs into a mountain and the mountain's attached to the Earth, and this predicts that the ball should be ejected into space, that's just not the case. The ball, it's just not true.
Well, I guess we'll just have to agree to disagree on that, man, because one half mv squared versus one half capital MV squared, and they make different KEs. So
Yeah.
yeah.
Yeah. Are you thinking of an inelastic collision where like a bird flies into a mountain and is pancaked against the side, instead of an elastic collision where it like bounces off as a hard object? Is that what you're thinking about, or no? I can't hear you if you're talking. I've probably spoken too much anyway, and I said I was tired.
I'm glad we got you enthusiastic, bro. It was a great build. Unfortunately, I think Dr. Bennett had to go. I wanted him to lay out his challenge, and I don't know if he fully was able to do that. Did you hear some of that from earlier?
Well, I think I beat him on the bedtime challenge.
Yeah, I'll get him to type out
Maybe
something for tomorrow, and we'll get it officially posted because now, people have reached out to contribute to the pot. It's now at $1,050. So we'll get an official thing written out and posted up for how to participate.
Hey, and just to be clear for everybody listening, this isn't a Flat Earth gathering money or any Flat Earth Fridays gathering money. What's happening is the level heads are contributing to the scientific community as a challenge. Like, hey, here's a challenge. Here's a reward if you could refute Dr. Bennett's position. So this isn't any of us, taking any money or anything like that. Yeah, I didn't even know that they were going to do that. I think Alan is touching base with some of the level heads and some of the space auditors over in YouTube land. And they're just contributing to the reward to make the challenge more enticing for the scientific community to acknowledge.
So you're saying if I go through the aggravation of disproving what he's put forward, I get $1,000?
Yes, sir.
1,000 and what is it?
1,050.
1,050, and I think Dr. Bennett said earlier that it's a $5 entry fee, so we know that you're serious.
Oh, I knew it. I knew there was a catch.
Nice little ratio.
And if no one beats the challenge, does the money go to charity or?
No, the money goes back to everyone that already gave me money. In fact, if you hear this challenge and you're like watching this later and you're like, oh, I want to give money, don't hold it and then just send me a DM and say, hey, I have the money, and add it to the thing. I don't want to hold your money, but it'll all be returned within the refund period. I have 30 days to refund it. So when it gets to day 25, if no one's participated or whatever, sending it all back.
Okay, well, I'm going to bow out, but I'll give you or Alan or Piezo or whoever the last word. But I'm going to say thank you for the discussion and say goodnight. But I'll wait for you guys to have the last word, so it's not like I'm just hitting the eject button.
No worries, lad. Thanks for the discussion. It was really nice to have you on. Much appreciated. Look forward to having you on in the future.
Yeah, absolutely, man. These are the type of discussions we try to have on a weekly basis. We know that the term flat Earth usually has negative connotations, but truly, man, we're really just here discussing the sciences, and we're really here trying to get to, the meat and potatoes, the crux of the matters, and making sure that everything's on the up and up. Going through the history, going through the science, going through the physics, and trying to have that higher level of discussion. Because I think no matter what you appeal to, what you believe in, what truth you may hold to yourself, what we're trying to do is find the truth and establish that. And we're only going to be able to do that by having that dialogue. So for anybody that's here for your first time, this is what it's like. This is what Flat Earth Fridays is. And it's a dope conversation to have when we can build together and extract that value. So I appreciate Mick Lyon for pulling up. Like I said, the last time that we had a conversation, we went into a little bit of red shift anomalies, and there was a great broad discussion over in his space. And it was just a pleasure to have him over here this evening. And hopefully we get to see you again, bro. Proud, you want to say something?
Yeah, actually I did. Can you guys hear me?
Loud and clear.
Yeah, Lying was saying that he basically, got the PhD, but he didn't pursue it. So I just kind of wanted to ask, what got you into science enough to go through to get your PhD, but not actually pursue a career or work in that field, if you don't mind me asking?
Oh, that's a long question, but I went into science because I love science and I love physics and I love biology too. And I still love science and physics, but my career took me in a different direction. I ended up going into industry, and I used some of those skills in industry. But uh, after I published some academic research, but I ended up working in some companies where I no longer published academic research and just kept climbing the ranks and was successful at that. So kept doing it.
That's awesome, man. What was your first impression of Flatter Fridays, Megline?
Well, I thought I would regret it.
But now you're
Um,
addicted and you want to come every Friday now.
Wait, is that a failed prediction? Did we get a failed prediction?
I don't know. I don't know. If I don't look at the clock, maybe it's okay.
Hey, man. Well, welcome to the lab frame. We're gonna stay in the lab frame, and like I said, man, you're always welcome. We always have an open mic for you. We love the discussion. And if you have anybody else within your community, I know you. I haven't seen you do a space in a while. But yeah, if you know anybody else, man, feel free to bring them by. Let them know what it's like.
Yeah, it's been a while since I've done a space. I've kind of moved to Blue Sky for the most part, but you tweeted at me and I saw that, so I stopped and said hi. Yeah, I appreciate having me on, and I hope I didn't hog the mic too much. So thanks.
No, man, this is you were very cordial. We like that, like open back and forth. The interjections was perfect. You treat everybody with respect. Hopefully, you feel the same way. And this is just a demonstration for the audience of how very opposing ideas can still have that build without like being toxic. And this is how it should be all the time. So I appreciate you contributing to that demonstration, bro.
Yeah, you come back, you can pick a topic.
Stationary Saturdays in some parts of the plane. I feel bad that we didn't get to say bye to Bennett. It sounded like he was having some mic issues, but I know we'll see him again in Discord or something.
Yeah, for sure. He'll be back in the morning.
It's okay. It's past his bedtime.
Dude, it's right around that time. I was just looking at the clock like, oh shit, he's about to set a record. I think the last time he was on here, he was actually up to like 1:30 though. Is it Stationary Saturdays?
It is.
Music
No,
intermission?
No, 15 minutes. 15 minutes till it's
Oh,
it's
nice,
not
nice.
stationary Saturdays here for 15 minutes. You got to give
Dude.
us Central Standard Time, lads. 15.
Sorry, sorry, reference frame.
I was listening very carefully to the intro music and I did not hear Flat Around. I'm just saying. Just saying.
Oh, we might have to go into a little intermission and spin some level sounds.
Run it, man. I missed the intro anyways, man. I had some IRL stuff going on. So yeah, let's go.
Oh yeah. We could say hi to some of the people, some of the mics, and then we could do an intermission before we get to the Witsit breakdown.